My name is Chris Modrich. I am the Valve Product Specialist for Lessman Instrument Company. I'd like to thank you all for taking the time out of your busy schedules to join us on our best practices in pressure instrumentation isolation webinar today. Ed has 40 years experience in the installation and use of Anderson-Greenwood instrument valves, and he currently serves as Director of Business Development for Emerson's Anderson-Greenwood products. He specializes in sales and marketing and product management. With all that said, Ed, it's all yours, sir.
All right. Well, thank you very much, and I appreciate everybody's time to participate in this afternoon. Hopefully we'll answer those questions. And we're going to do this a little differently, and let me show you what it's going to be like. So our agenda, or my agenda to run through, is we're going to specifically focus on differential pressure manifolds today. And we're going to talk about a little bit about what makes a valve, as well as some of the industry-changing things that are happening for alternative designs. And at the very end, we'll hit a couple of slides on things that you really need to consider when you're deciding on buying or speccing an instrument manifold. So as he said, this is me. You know, you always hate to look at photos because you realize just how old you are. And so that's one. I wasn't even doing a selfie there. Somebody else took it. But what I want you to note on here is the email address and the phone number. Certainly, Lessman is always available with their expertise, but that's just a contact point for me as well. So we'll blow on from there. Just very quickly, precision fluid control is what I am a part of, and basically that's the TESCOM, Anderson-Greenwood instrument line. We were acquired by Emerson about 2 years ago, and because of the specialty nature of the regulators for the TESCOM makes, they decided that we would be a good fit together, and we have been. So that's been in place for a while. As mentioned earlier, I've been associated with the instrumentation product line for 40 years now, and that's through different companies along the way. So just briefly, this is the kind of things that TESCOM products that they make for instrumentation: the manifolds, the instrument valves, which include primary isolation valves, hand valves, gauge valves, and instrumentation protection systems, which are the enclosures. And so again, we're going to focus on manifolds and particularly talk about what's necessary with manifolds, as well as some of the details of how we got there with manifolds, so you understand them better when you're buying or speccing. So first of all, just very quickly, I'm going to run through this because it doesn't matter whether it's a manifold, gauge valve, hand valve, whatever. What is it that makes an instrument valve a valve or a manifold come into place for service with measurement systems? And first and foremost is that the valves are shut-off isolation valves in dead-ended service. They're not necessarily for metering or controlling the flow. And as you know, if you put in a pressure gauge or a differential pressure transmitter, I mean, it's a dead-end service. They're not there. So you're looking for bubble-tight shut-off in isolation, equalization, and venting. And you get that by utilizing these valves in that type of service, because we're not talking about high cycle life, but you also have a premium on seats and bond assemblies, things like that, that give you a bubble-tight shut-off. Because if there is any leakage, particularly in differential pressure measurement, it can cause an error, whether you're doing custody transfer, which is really severe, or you're just trying to do repeatability because you're in a process plant controlling things. So bubble-tight shut-off is key. The other things that make up an instrument valve, in particular manifold, is we're trying to eliminate the number of leak points. Any leakage can cause an error in the measurement. So we do that through trying to put as many things into one valve body as we can and eliminating all those connection points. As a manifold, and an instrument manifold in particular, you got to be able to mount up to every or anybody's measurement device that are produced out there. We're going to talk about that today. And we want to facilitate, particularly with the manifold, the ability to calibrate in the field. Typically that doesn't always happen, but certainly testing the manifold and or doing a verification does happen. And last but not least, what we do and other people do as well when we're building manifolds is that we're trying to reduce weight and reduce the envelope size so it maximizes the real estate that the customer you all are putting things into. So what you see here is a slice. It's a slice. These are 3-valve, 5-valve, 2 different 5-valve manifold styles. And just this breadth of products that I put down here on the bottom, it represents only a portion of the different manifolds we make. And so they come in a variety of sizes, shapes, inlets, outlets, seating types, packing types as well. And so what we're going to do today, we'll start off by why you need a manifold to begin with. Back around the turn of the last century, I have to say now, in the 1800s, natural gas became a commodity that needed to be measured to be able to be sold. And so orifice plate measurement, differential pressure measurement became the standard which that was done by, and then utilizing the Bernoulli theorem. So what you see right here is a typical orifice meter run. You've got a gas, in this case, going down the pipe. There's an orifice plate in the middle of it between these 2 flanges, and the hole is reducing the bore. So the gas has to push through faster at a higher volume. And what that does is it causes a pressure drop. And as you see here in the charts, this is around 100 pounds or so, and it's sitting there. When it hits the orifice plate, the pressure immediately drops a few inches of water column, basically. And as the velocity of the gas slows down, then what happens, it starts recovering some of the pressure, but certainly not all of it. But that's a typical orifice meter run. And what happened back in the 1800s, early 1900s, is that the differential pressure across there, along with the temperature of the gas, as well as the upstream pressure, you could do a calculation to come up with flow. And so if I knew the flow, then certainly I could charge for the gas going through it, going to a customer. So this is a primary way of making those measurements. And today, it still is probably about 40 to 55% of the measurement done out there is with orifice plate measurement, just like this. So it can be any kind of differential device. And the first ones that were developed were bellows style. And that's what you see here at the bottom of the page. So you have pressure coming in on one side of the bellows, pressure coming in on the other side. And if it's 6,000 pounds, which it wasn't back then, but if it was 6,000 pounds pressure, you'd have 6,000 PSI on one side and you'd have 5,999 on the other. So the only difference that makes this bellows move is that small differential pressure, which is what you're trying to pick up upon and measure and get a good measurement on. So the picture you see here of circular case recorders, because those are the first ones that were used. These are clock keyed charts that turn through the day or week or month even. And below it is the first manifolds that were produced, and that's what you see at the bottom. One of these are needle valve, the other ones were plug cocks. Well, when they had these kind of manifolds, and as we were saying before, it's absolutely imperative that you don't have leakage. And so a 3-valve manifold in the style type that they had in the old days, if you will, weren't very good valves and they would leak. Well, 2 things happen when they leak. One of them is it shows a lower flow rate because I'm not having a high differential on the instrument side. And the other thing is it's bringing the process, in this case natural gas, but it could be any process in the future. It can bring it up into the manifold, and instead of being a dead-ended service, now because this equalizing valve, the center valve, leaks, it would cause flow. And so I'm going to say this now, that obviously it causes the error in the measurement, but it also brings whatever the temperature is up in from the piping into the manifold, which can damage the instrument itself. But this is a typical example. Normally in operation, the equalizer valve is closed, the 2 lock valves are open. When you do a 0, and think of this as well, if I've got an installation in place like this, and I think I have an error, the first thing I can go do is a zeroing function, because I've got pressure, I've got temperature in the pipe, I've got environmental temperature as well. And so I can simulate a no-flow condition, even though there's still gas flowing in the pipe, but letting it continue on, I can simulate a no-flow condition by closing off the downstream side, which is represented by this low pressure valve, and open up the equalizer or the centering valve here in the middle. So now I can have both sides looking at the same pressure, which is this upstream side. Well, then I can go back to the instrument and I can look, and if it's not sitting on 0, then I know I have a problem. So the primary function of a manifold is two things. It's one, to isolate, and it's also to do a calibration or an instrument check. Well, in the case of these, back in those old days, they had these valves leaked, so they're always having a problem. So some person way back there when came up with, we call it a 5-valve gas manifold, but you could also call it a double block and bleed. So the high and the low side pressure isolation valves were always open, but they put two equalizing block valves here and here, so that if one of them began to leak, the leakage would simply go through this equalizing vent valve, which was always open, out to the atmosphere. Well, there's enough capacity that it continues to allow the measurement device to continue to work. But the guys out in the field, people out in the field that went out to check them, I mean, when they go up to one of these and look at them, because they're always checking them about once a week or even more, they'd smell it to see if there's any gas coming out this valve, or you lick their finger and stick over the end of the valve to see if it would bubble. If it was, they knew that they would have to go in and change out these valves. But it gave them time for very bad valves to continue accurately measuring the natural gas, as opposed to a standard 3-valve design that you see over here. So therein lies how things were done and how the first manifolds got developed. They're all hard piped, just like you see here. And up until about 10 years ago, you could still probably see a lot of these circular case recorders. One pin's for differential, one's for temperature, and one is for the upstream pressure side. But this is mostly common, hand valves, and as I said earlier, okay, the valves may or may not work very well, but at least this way they can continue with their measurement. So what happened over time is, certainly this was out there and in place. Most plants and operations back before the 50s were spread out, and they could use circular case recorders to measure flow, not just for custody transfer in terms of charging for the gas, but also to be able to, in a plant situation, get repeatability when the measurement would go through at a certain point, and they tried to balance out their plant in its process conditions. So really two items. Well, in the 50s, as you can see there on the right, the first pneumatic transmitter was built, because after the World War II, you had all these circular case recorders in rubber plants. They were sitting side by side, so it makes it really difficult for the operations folks to see what's going on without running up and down the line. So the pressure transmitter, pneumatic pressure transmitter, allowed a signal of 3 to 15 psi to be taken back to the control room with a small gauge lined up against each other, so the operators themselves could see what was going on and do it in a much easier manner than trying to control everything about a big old circular case recorder. The only thing about this transmitter is that with the pneumatic, you had a capsule instead of bellows now, and you had pressure coming on both sides, and the sensitivity is that moving in those inches of water column that are the differential that's created. There's a force bar pneumatic amplifier, and that's where you got the 3 to 15 psi signal. And also the 3 pounds meant that I knew that the transmitter was in operation, wasn't dead, so that's why they went to 3 to 15 psi. Well, as that went along, what you see in this photograph here is one of the first pneumatic transmitters that were put in. This again is back in the late 50s, probably up in Borger, Texas, a refinery up there. But the first manifolds, again, were hard piped. And you can see they're doing either gate or globe valves. They're into the Orifice taps right off the line. They have bull plugs out here because they like rotability, probably a gate valve then. But every one of these points, all of the stuff with union coupling and threaded and elbows and the rest, it cost a lot of money to put this thing together, and you had problems with leakage as well. So let's step on. So the thing that's interesting about manifolds, they're designed to a certain size and connection size of the rest, and this happens to be the first reason why they are in the size that they are. This is a typical orifice flange union. There's the plate in between, the gaskets on the outside. A typical orifice plate union has 3/8" orifices through it, tapped down into the flange itself. And these are typically also 1/2" threaded taps. But this A dimension that you see right here, turns out it's 2 1/8". And you have to remember that. So the center to center line of those two taps are 2 1/8". They will vary a little bit depending on the thickness of the plate and maybe the gasket. But that's the first thing that ultimately wound up being part of the design of manifolds. This gets a little bit better look. There's a 2 1/8" center to center. And oh, by the way, as I said, they mostly are 2 1/8" center to center. But if you got a hard pipe and it's off a little bit, there are nipples and other things built in so that they were eccentric. In other words, the inlet side and the outlet side of a nipple wasn't straight lined. It was off-centered just a bit. And you could move those around to make sure you make up for that 2 1/8" center. The other thing that was done, like you see on the pneumatic transmitter down here, these are 2-bolt connectors. You can see the 2 bolts, and I'll show this picture again in a minute. But basically, that 2-bolt connector was a flanged, gasketed surface to the transmitter itself. And the holes inside that you see here were also eccentric. So I could flip these things around, and I could absorb some of that little bit of differences off the 2 1/8" centers. The other fact is I could take the transmitter off without having removing any piping. So in the old days, on the old transmitters, there was a lot of work and maintenance on them. That was extremely a benefit. But these are 2-bolt connectors, footballs as we call them in North America, and they're called kidney flanges in Europe. So the first manifold, this is what you're looking at right here. It was designed so the inlets were on 2 1/8" centers, and the outlets were too. So this one was hard piped even still to a pneumatic transmitter. The inlet side, this is the hard pipe. They had 2-bolt connectors on the inlet side so they could get it tight and up close. It was mounted directly so that in this case, in the old days, the hydrocarbons were a lot heavier. They didn't want anything freezing of the hydrocarbons, if you will, in the manifold. And this provided that kind of installation. Yes, it was still hard pipe, but now you got fewer leak points because all those connections are built into the manifold. It's less expensive to install and also less expensive to maintain. You see these 2 plugs back here. If you remove them, you could put a rod out tool when the line is shut down to make sure you got any plugging or freezing material at ambient temperatures. One thing about this is you notice that the transmitter's hanging down below the manifold, and that's typical of a system where you have fluids in it and not gases. And these vents that are up here on top, when you commission a transmitter into service, if it's liquids, I want it all liquid. And so that's why it's hanging below. And I have vents up here so I can open it up and make sure I blow all the gas out if there's any gas bubbles trapped. The same thing goes with gas. I want all gas, whatever kind of gas it is. And so typically the transmitter would be mounted coming straight out or actually above the manifold. And there would be plugs again to be able during commissioning to drain all the liquids out of it. So these were hard pipe. They're basically the first generation of manifolds. And as time went by and the hydrocarbons became lighter, they weren't concerned anymore necessarily with having larger orifices in the manifold, and they could do more compact. And they could also mount the manifold and the transmitter right off the packing. Maybe if you have in this case, an elevated piping rack, I can mount it at the ground level to be able to maintain or check out the transmitter with the manifold and do it easily without getting on a ladder. So a couple of things here. When that happened, we started utilizing a flange surface so that it could mount up to the flange surface of a transmitter. And that's exactly what you see here. The idea was just like having gasketed surfaces between two flanges. The gasket sits here on inside of a gasket groove, and there's 4 bolts that mount these together. So that was the start, and also for remote mounting and the style of manifolds that came out with that. The next big thing that changed is pneumatics lasted for a while, but eventually electronics came into being because it was less expensive to run the conduit lines over back to the control room, obviously, because now they're wired, a lot more flexibility. But the part of it didn't change. The bottom works of the transmitters didn't change. In this case, I've got diaphragms on either side. I've got clamshells that bolt up to it. When I put them together, then I have a flange-faced outlet. And to this day, when these kind of transmitters, there's still a 2-bolt connector. There you can see it, and I know it'd probably be a little difficult, but you can see that the inlet hole of the 2-bolt connector of the football is off to one side. It's a straight-through hole mounting straight up to the hole on the transmitter face. There's the gasket, and there's the 2 bolts. So the 2-bolt connector was in place. And now I've got most of the manifolds that I make, although they can be still pipe to pipe, they have flange connections on the outlet side, particularly to mount up to a transmitter. The only other things that changed too was there was also a change in that instead of mounting up the transmitter, now I've got the manifolds that are out there and I mount everything to them. So the good news is, like those footballs I talked about before, now all I got to do is remove these 4 bolts and I can take the transmitter away and do any kind of work on it, because I've got a mounting bracket on a 2-inch pipe stand, for an example, or other means. And all this gets left in place, the valving, the tubing, everything, so that the transmitter can swing free. And then when I'm building something new, I can go out and put all of this in place, do all my testing of the piping, and then bring the transmitter out later. So that's where we got to with the designs, and all the way through the 70s and most of the 80s. The other thing that came along is that in the power industry, they always wanted to be able to reduce anything associated with steam or the condensate from steam. So they went to a 5-valve power vent. So here's a 3-valve that we started with on the configuration. Here's the 5-valve gas pattern or double block and bleed equalizer. And now we go to a 5-valve power vent. The reason I wanted to do this is you never blow steam all the way through the manifold, because number one, it heats up and can cause damage to the transmitter, plus all the crud and stuff that develops in the impulse lines, the tubing or the hard piping that comes to the manifold. So what they wanted to be able to do, though, is to provide individual valves to blow down between the block valve on the manifold and the instrument itself. And that's why there's 2 separate valves there. Just in case the block valve was leaking, they wanted that belt and suspenders approach. Well, it turns out that is going forward, this particular configuration is good for something else as well, just besides the power industry wanting to have one like this. It was made the ability that, because of the environmental issues that we now have, is now I have the ability to drain either one of these sides, to vent them into a header, to a bucket, whatever it may be. So it's being used more and more. A 5-valve power vent is what we call it. So that's the other configuration that came into place. When you're looking at manifolds, for an example, what you have here, I mean, this is a 5-valve gas pattern, and this is a 5-valve power vent pattern. Well, it's kind of hard to tell the difference, but normally the 5-valve gas pattern has smaller valves for the double block and bleed function of the equalizer, as opposed to a power vent, which normally is using full service, larger bond assemblies, because there's higher pressures, higher temperatures to be involved as well. So we'll go back here for just a second. Again, here's the typical 5-valve with a circular case recorder. And the reason I bring this up, here's the old bellows. Well, it's a hard time to change your mind, particularly the measurement folks, because they're so worried with the accuracy of the measurement. But in the late 80s, the AGA and other folks decided that, well, maybe it was okay to use electronic measurement devices. So the basic, what you see here is an electronic measurement device, wound up moving into flow computers and other things. And what that brought on was the fact that now all of a sudden they could see things that they hadn't seen before in their measurement. So the circular case recorders have a pin. That pin marks on a chart, and it's a pretty wide mark that's on the chart. And so a 1% error rate was more than acceptable, and you couldn't see it any finer. Well, when the electronics came into being, all of a sudden they were looking at this, a lot of noise. They could see the measurement and the differential pressure down in the tenths, hundreds, and thousands. So they saw something that got them at their attention, in that when you have pulsating flow, in particular natural gas, pulsating flow going down the line, it's not that you're flowing through these impulse lines into the measurement device, but it is the fact that that pulsation is beating and going to the transmitter. So if I take a measurement right here off the orifice taps themselves, it's pretty smooth, but you see the pulsation, but it's a much more accurate measurement. When you have all the noise in it, like you see here, you get an attenuation of the signal. And so if I averaged all these out, or looked at the measurement that way to charge somebody for the gas, in this case, it's going to show that I'm selling them more gas than I'm actually giving to them. So there was an immediate change in the natural gas industry, particularly on the custody transfer side, and they went to this. They found out, number one, they needed to be as close to this tap as they could. They needed to have 3/8-inch orifice, never any changes of the orifice size. So when you went up here and go into tubing and the rest, you get larger orifices, smaller orifices. You go through the manifold, you get smaller orifices, and you open up into a big open area that's in the transmitter. And so that's what caused the ringing effect, as I had pulsation moving up and down. So the solution was, I want to mount everything right off those orifice taps. I want 3/8-inch orifice. I want it straight through, right to the differential pressure transmitter. So as close as I can get it. And natural gas mounting went back to direct mounting instead of remote again, just like it had started out doing. And so to be able to hang all this material and the rest, because you're looking at 40, 50 pounds, plus going all through the kind of different valves and the rest, there was a device that was also invented, because those taps on the orifice flange union are only 1/2 inch. And if you put 50, 60 pounds of weight hanging out there on a moment arm that's large, they can break. So the stabilized football was put into place. It moved the moment arm further out, and it could support all the weight. So that made it comfortable for the natural gas folks. If they didn't have a vertical connection they could use, where you're mounting everything straight up, then they could at least do a horizontal and utilize the stabilized football to be able to support the weight while still giving the 3/8-inch orifice straight through. That caused all kinds of things. Everybody wanted their own designs, different kinds of manifolds, but all with 3/8-inch large orifices. In this case, you had a single point takeoff here, and the customer has his own set of measurement devices. The seller has his own, putting flow controllers on, flow meters on the piping as well, and duplicating it. All that became and went along with the going back to direct mount on natural gas industry. The next big change was what you see here. It was a coplanar style transmitter. So this design changed everything in terms of how you mounted a manifold to a transmitter. First of all, you see it's in a position that there is the inlet coming from the bottom. There is a coplanar adapter flange. We'll show it in just a second. And then going into a coplanar design, meaning that the two diaphragms are side by side in the same plane rather than opposite of each other. And this is kind of what it looks like. This is a little picture. This happens to be, I guess, a Yokogawa, a Honeywell, and a Rosemont. But this Rosemont has a traditional flange, and I'll show you on it in just a minute. The transmitter itself looked like this. So this coplanar adapter flange had to be bolted onto the transmitter, because on the transmitter side, the two diaphragms were basically 1.33 inches apart. But to go with the industry standard of 2 1/8 inch, this coplanar adapter gave it that capability. And also, by the way, here's the bleed plugs for commissioning service. This is what they look like on the inside. You can see the two diaphragms side by side. That's the gasketing system that they use. There's that 1.33 inches, say, center to center. The bolts on here go all the way through, holding it on, and on the opposite side, it's 2 1/8. In the beginning, this is how we had to address it, and everybody else did too. You could still use a normal 3-valve manifold that had a flange gasket on it, but we had longer bolts, and the bolts would go through the manifold flange, through the coplanar adapter flange, and into the transmitter and hang on to it. Some people didn't like the idea that always had to mount this in an upper position, so the traditional flange, Rosemont offered that as well. This is a flange, kind of looks like the body of a regular manifold, but the transmitter is mounted onto it with that 1.25 inches center to center to accommodate the flanges. But then the flange connection that goes to the manifold is back on 2 1/8 inch centers, but it can allow a transmitter, or excuse me, a manifold to be mounted directly up to it, with the transmitter still being in the upper position. So that started the solving of the need for a little bit different designs, particularly with the Rosemont transmitter. What happened next is eliminate leak points. So the first thing that was done was get rid of the coplanar adapter flange and simply take the manifold and put 1.33 inches center to center on the back side and 2 1/8 inch on the inlet side. And so that's the integral manifold. Here you see these are the MT manifolds, and it simply does the same thing like the traditional flange I just talked about a minute ago, except that we put valves into it. So you can get a 2-valve, 3-valve, and other configuration designs. That's kind of a combination of different things that people do for the manifolds. The next thing that happened in the industry is this happened back in the mid-90s in particular. A lot of customers came out, particularly in the process side, they did not want to have impulse lines. So the tubing and the fittings that were used to put everything remotely mounted. And the reason for that is no wetted threads. There's a real concern on MPT threads. MPT threads, sometimes if the male end thread is large and female thread, like on a body of a valve, it's smaller diameter, still within the tolerances, you don't get a lot of engagement between the two threads. So no wetted threads, no impulse lines, because they tend to hold up liquids or gases or dirt or other things that may come out of the process and sit there and cause error measurements. They also are looking for bigger standard bore sizes. This is the process industry now, to prevent plugging and straight through connections as well. The only way you can take care of these two is by doing direct mounting. So voila, they're back into doing direct mounting off the orifice taps. Some folks wanted double block and bleed primary block valves if they're going to direct mount for safety and operations. Then concerns became a weight in packaging and testing. I'm going to show you some valves and what that does and what they look like. This is one way to do it. It provided direct mounting, but it takes multiple sets, if you will, of manifolds to do that, but it supports all the weight and the rest. The process goes straight through. You can do higher temperature, higher pressure as well. Another design, these are using those stabilized footballs, but in the process side, they may not be looking for a 5-valve gas pattern, but this isn't untypical as well. So with that in mind, people are still to this day coming up with different manifold configurations. They're not hugely popular, but we, as well as others, try to conform to those. And what you see here is a double block equalizing manifold. And so it has 2 block valves for safety of the operator. If one of these valves doesn't work, then you've got a secondary valve, the equalizing valve. So it functions like a 3-valve manifold, and then it can have bleed valves on either side of it as well, or be able to put some type of a measurement, calibrated measurement in there to check the transmitter without removing it. So let me go through a little bit of a review real quick. So if you're selecting a DP manifold, differential pressure manifold, you need to know what configurations you want. A 3-valve. There's also a 4-valve version, which is nothing more than a 3-valve, but has a separate valve coming out of it for a control bleed. So a 3-valve. The bulk of the valves that we sell, for an example, are still basically 3-valve manifolds, because number one, the valves are bubble tight, shut off, repeatable, long life, and so most customers still go with that way. There's a 5-valve pattern, double block and bleed, equalizing the natural gas version. The folks that have those valves, it doesn't always have to be for natural gas. It can be for any service. It's what they're used to, what they desire to be able to do isolation as well as calibration in the field. And then there's a 5-valve pattern power vent. And as I said, that's the growing version. It enables you to vent for environmental concerns and issues. The next thing you got to know, as we just pointed out, you got to know the transmitter style. What kind of transmitter is it? And it's best to know what kind of manufacturer, so you can relate that to people who are trying to provide you something. And it also has an impact on how you're going to do your installation into the line. The other thing is connections. There's an installation type, and you need to think about direct or remote. That's also going to impact what your connections are onto the manifold design itself, depending on if it could be direct and you're going to go flange by flange, or you're going to go pipe by pipe, or you're going to go pipe by flange. And what I mean by that, when we say pipe by pipe, that means the inlets and outlets can be a 1/4 inch, but most of the time they're 1/2 inch NPT connections, and they could be socket weld as well. The pipe by flange is the remote mounted manifold I showed first. The flange side goes to the instrument, and it has a pipe inlet. So you could screw tube fittings into it, the hard pipe into it, and it could come in other varieties such as socket weld, female socket weld inlets. And then there's a flange by flange version. So basically with the flange by flange version, certainly the outlet side of the flange bolting up to the transmitter. The inlet side may use the 2-bolt connectors to connect up to the inlet flange, because they mirror, again, that inlet flange mirrors what's on the transmitter. Why would you want to do that in this day and age? Well, get rid of those threaded connections, because all I've got to do now is remove those 2-bolt connectors, and I don't have to disturb the thread. Because once you start making up and putting back together NPT threads, you run the risk of the potential of some kind of leakage. Operating conditions are always important. You need to know what the temperature and pressure is. And the temperature and pressure is going to dictate if you use a soft seat or metal seat. The bulk of our manifolds that we sell are metal seated, except for natural gas. They like soft seats. But they're more universal with the metal seat in that you don't have to worry about a particular temperature, as most of these are rated up to 1,000 degrees. So the first question you might ask yourself, as long as we're talking about that, is that why do I need a device that's the manifold rated to 1,000 degrees, and the instrument transmitters, their top end is 180 degrees? Well, it goes back to the thing I just said earlier. If you do with a 3-valve manifold, if you did not close off that equalizer valve between the 2 lines, you're going to have flow. And if you have flow, it's going to cause the process, if it's 600, 700 degrees, to heat up the manifold, which in turn is going to heat up the transmitter. So not a good thing. So it's got to be rated at the top rating or the rating of the piping itself, which may be 1,000 degrees, so that the packing and everything else survives. You don't have leakage caused by the manifold, even though you may be destroying the transmitter, but it can operate under those kind of conditions. Softer metal seat, if you really have a dirty service, a lot of particles in it, soft seats are better because it will tend to push those particles into the seat. And then the metal seat, it can work well, but not as well as the soft seat. And then you have exotic, fluids or fluids that are going to require exotic materials. Orifice size is important, as I just said, for the very reason of what kind of services the manifold's in. Standard for us is 3/16 inch orifice, but you can go up to a 3/8 inch orifice, the smallest port within the valve body. Bolt selection is important too. A lot of time we don't talk about this much. For us, the standard bolt that you get to hook or to make the transmitter to the manifold flange is a B7, which is a carbon steel bolt. You have a lot of strength there, and it can handle the 6,000 psi pressure ratings of the manifold, even with the transmitter maybe not going that high. If you order 3/16 stainless steel bolt and don't order anything special with it, the yield strength of a 3/16 stainless steel bolt in this size is such that when you put it up to as much as 4,500 pounds, it'll hold, but it will stretch above 4,500 pounds. What happens? Great, you put everything together, you put the manifold and the transmitter together using a 3/16 stainless steel valve, you go up to pressure, it sits there over time, you bring the system down, and what's happened is, when it's above 4,500 psi, the bolt's already stretched, so unless you go out and retighten it again, it's going to leak when you go back up into service. So you're always going to be fighting that battle. I've seen it many times. So 3/16 is fine as long as you're below 4,500 pounds. What we do is we derate the manifold if you order it that way to 4,500 pounds. If you have to have 3/16 stainless steel and you need the tensile strength as we're talking about that's not available in 3/16 plain material, then we provide B8M Class 2 strained hardened bolts that get you to the full rating of the manifold and the transmitter as well. The last thing I want to talk about is the problem that occurs far too often. And part of it's because, the expertise that's in the field on the maintenance side. We have been called to actually do seminars on this, and that is when you mount the manifold up to a transmitter, it is imperative that you do it correctly, or you're going to have a leak. And as it says there, the bolts that we utilize, all those we just talked about, you're torquing in between 28 and 32 foot-pounds at the end torque that you put to hold the flange to the transmitter flange. If you don't use an X pattern, as it says here, and you tighten down one side, then what's going to happen is that gasket on the tightened side is just going to squeeze out the end or somewhere else and not be bubble tight. So the means by which you put things together is you put the manifold and the transmitter together. You do a finger tight X pattern to start. You go half of the torque value for the next X pattern on the manifold, and then fully at full pass with full torque at the end. If you know people are doing this, I've seen, like I said, a whole bunch of these that don't get put together right. It's a necessary part to make a good seal. By the way, that's black because it is graphite. We use Teflon, and we also use O-rings. Just so again, as a wrap up, we do 3-valve, 4-valve, 5-valve, 5-valve power and vent, and 5-valve natural gas. If you look below, there's just another sampling of manifolds that you didn't see the first time around. So that gets me to my 45 minutes plus 5, I see, because we started a little bit late. Certainly we're interested in any questions, and if you have questions, we'd love to have them. We would, any situation that you run into with a differential pressure manager, if I didn't address it, we'd certainly like to hear it. So gentlemen, Lessman folks, it's back to you.
Okay, Ed, it's Chris. A couple of questions got typed in.
Okay.
Raymond would like to know if this presentation is available in PDF.
It can be.
Okay.
Right now it's just in PowerPoint, but we'll work on that.
Okay. And Nestor has a couple of questions. When doing the zeroing process, which side of the transmitter gives a better result, the high side or the low side?
Good question. I didn't put it in there, but you always want to leave the high side open and the low side closed. That's the standard that the industry use, because you don't know what's going to be going on the other side of the orifice plate. You know, you get a little dribble. The high side is more consistent, so you want to leave the high side valve open and close the low side, and then open up slowly your equalizer valve. Because one of the things you need to know is that if you do a sudden pressure release onto the diaphragms, there's still a potential to cause them to be damaged. And I'd like to say one more thing with that. No matter what, every transmitter is a mechanical device on the diaphragm side. So it's subject to temperature and it's subject to pressure. There's algorithms that are built into the electronics of the transmitters nowadays to try to accommodate and take into consideration, but it's still a mechanical device. So zeroing is still done. Maybe not as much as it used to be in the old days when the transmitter was really bad, but a manifold allows you to do that besides the isolation to be able to take the device off. Next question.
Great. Another question from Nestor. Could you please repeat the difference between the gas pattern and the Power Vent 5 manifold?
Sure. I'll just use this one. Okay. The gas pattern is what you see right here. Hopefully you can see my arrow moving around. The gas pattern still has two isolation valves, but instead of having a single valve for the equalizer, you have this double block and bleed configuration that performs the same task. So and the reason why is because people were concerned about the validity of how well the valves are holding against leakage. So if one of these valves happens to start to leak, chances are the other one's not, then any leakage would go through the vent valve to the atmosphere. And the capacity is enough to continue to keep your measurement right. Because if it was just an equalizing valve, as we just talked about, and it started to open, well, what's going to happen is you're going to sense it against the measurement device. So that's the 5-valve gas pattern or double block equalizer valve. For the vent, it's just like having a 3-valve manifold, equalizer, 2-block valves. You stick additional valves on the transmitter side downstream of the block valves so that if you close everything off, you can open up and drain any of the fluid or the gases that are between the block valve and the equalizing valve. You can even open up the equalizing valve and drain off both sides. That drain basically goes to, like I said, a bucket or a header if you need to capture it. But then you can also, when you do calibration, you can close the low side block valve and the high side. You can close the zeroing valve, the equalizing valve in the middle, and open up these two valves. By doing that, you can leave this side open to atmosphere. It's what you want to do when you're checking the zero of the instrument or doing the calibration, and then open up this side and put a calibrated source in so you can actually span the instrument to see if it's reading right. Hopefully that answers the question.
Okay. That was it as far as written questions. I'm going to, there's not that many of us on the call here. I'm just going to put everybody's mics on for those that don't care to type. If anybody has any questions they'd like to ask via the phone or the computer, now would be your time to jump in. I'll leave a little silence here.
All right.
Okay. Doesn't seem we have any takers. So, Ed, thank you for sharing your presentation with us. It was excellent.
It was my pleasure. And differential pressure is not dead yet. So we're going to keep on using them, and we need good, experienced people that know how to use a manifold. Thank you, guys. Thanks, everybody.
Okay. For today's attendees, if you have any specific questions, feel free to give us a call at 800-9-LESSMAN, which is also 800-953-7626. If you don't know anybody in inside sales or your account manager, please ask for me. It's Chris Modrich, M-O-D-R-I-C-H, or you can email me at chrism@lessman. If you'd like to learn more about any of our technologies, we have lots of webinars posted on our website, lessman.com, and also they're on our YouTube channel at Lessman Instrument Company under YouTube. If there are any subjects that the attendees would be interested in learning more about, please shoot me an email. We're always looking for topics that people are interested in learning on. So at the end of all of this, Ed, thank you. Everybody who came, thank you. We appreciate your time and your efforts, and hope to see you at our next webinar. Have a good day, everybody.